So 3 is our next prime, and we now cross off all multiples. So you recall that a prime number is a number bigger than 1 that's only divisible by 1 and itself. And the first few primes look like this. And we can ask some basic questions about prime numbers. So the first question is, how do you find prime numbers? And one way is to use the sieve of Eratosthenes, where what you do is you write out all numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on, 20, 30, 40, and we keep going. And you cross off all the ones that aren't prime. Well, first of all, 0 and 1 don't count because 0 and 1 is a unit, and the first number you haven't crossed out is 2. So we write down 2 as a prime, and we then cross off all the multiples of 2, because these can't be prime. And the first number not on this list is 3. So 3 is our next prime, and we now cross off all multiples of 3. So we go 3, 6, 9, 12, 13, 14, 15, 18. So we cross them off like this. Hang on, missed out a few. It should be that one there and that one. And next, we look at the first number we haven't crossed out, and this number is now 5. So 5 is our next prime when we cross off all multiples of 5, which is easy because those are just those ones there. And then we get to 7, which is the first number not crossed out, and we cross off all multiples of 7, and actually all of these have already been crossed out except for that one there. And we can actually stop now because any bigger prime has a square bigger than 49, so it can't be the smallest prime divisible by a number. So what we've done is we've crossed off all numbers less than 50 that are not divisible by 2, 3, 5, and 7, where these are the primes less than the square root of 50. And if we look and see what numbers we've got left, we've got 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, and if you're doing number theory, you very soon learn all the primes up to about 100. So the next question is, how many primes are there? Well, if we look at this table, primes seem to be fairly common, and there's no sign of them suddenly stopping, and so this suggests that the number of primes should actually be infinite. And this is the first theorem of number theory due to Euclid. The number of primes is infinite. Well, actually, Euclid didn't say the number of primes is infinite because the Greeks didn't really like the concept of infinity. What Euclid actually said is something equivalent. He said that if you take any finite set of primes p1 up to pn, you can find another prime not in this set. And what he did was he took the product p1 times p2 and so on up to times pn, and you add 1 to it. And what we do is we take a prime factor pn plus 1 of this. And we notice the prime factor pn plus 1 can't be any of these primes p1 up to pn, because if it was p1 up to pn, then it would divide this number here, and it would also divide this number here, so it would have to divide 1. So pn plus 1 is a new prime. So let's just see how this works. We start off with all the primes we can think of, which is absolutely no primes at all because we haven't yet started yet. So we take the product of all the primes we thought of, which is actually 1, because this is the product of no primes. and then we add 1 to this, and we get our first prime, which is 2. You notice that if you take the product of an empty set of numbers, you get 1, for the same reason that if you take the sum of an empty set of numbers, you just get 0. So this is our first prime, and now we take the product of all the primes we've thought of so far, which is just 2, and we add 1 to this, and we get 3. And then we take the product of all the primes we thought of and add 1 to this, and we get 7. And that's prime, so we now take the product of all the primes we thought of and add 1 to this, and this gives us 43. And now we take 2 times 3 times 7 times 43 and add 1 to this, and this time it's not a prime, it's 1807, and this factors as 13 times 139. So our next new prime is actually 13. So it seems to be a common misunderstanding that if you take the product of all the primes you've thought of and add 1, then you get another prime. But this isn't actually true. I mean, it breaks down for the first time here. So this shows there are infinitely many primes. The next question is how to find large primes. There's a sort of game in played by number theorists where they sort of compete to see who can find the biggest prime. So how can you do this? Well, one good way is to look at things called Mersenne primes. These are named after Mersenne, who was the first person to discuss them. These are primes of the form 2 to the n minus 1. So let's have a look at a few of them, where we have 2 to the 2 minus 1, which is 3, and we can have 2 to the 3 minus 1, which is 7, or we can have 2 to the 4 minus 1. Well, this is 15, and it's not prime, which is it's 3 times 5. Well, you notice the problem here is that 4 isn't a prime, because 2 to the ab minus 1 is divisible by 2 to the a minus 1. This is 2 to the a minus 1 times 2 to the ab minus a plus various things up to plus 1. So if we want 2 to the n minus 1 to be prime, we should take n to be a prime. So we can speed it up by just looking at 2 to the primes minus 1. So we have 2 to the 5 minus 1, which is 31, and 2 to the 7 minus 1 is 127. And this seems to be a rather good way of generating primes, because you notice, whenever we take a prime and take 2 to the p minus 1, we always seem to get a prime. Well, this doesn't actually quite work, because if we go to 2 to the 11 minus 1, this is actually equal to 2047, which is just 23 times 199. So this doesn't always work. However, it's still a reasonably good way to generate primes. So 2 to the p minus 1 is quite often prime. We have an open problem. Are there infinitely many Mersenne primes? So no one really knows, although the answer is probably yes, for a reason I'll discuss later. So people have used computers to find large numbers of Mersenne primes. And in fact, there are very good tests to see if a very large number is a Mersenne prime, and you can actually test numbers with millions of digits to see if they're Mersenne primes. In fact, most of the time, the largest known prime is actually a Mersenne prime, because they're particularly easy to check. So another famous sort of prime are Fermat primes. Well, if we're going to look at primes of the form 2 to the n minus 1, we should also look at primes of the form 2 to the n plus 1. So let's look at the first few cases just to see what's going on. We have 2 to the 0 plus 1 is 2, 2 to the 1 plus 1 is 3, 2 to the 2 plus 1 is 5, 2 to the 3 plus 1 is, well, 2 to the 3 plus 1 is now 9. Now, that's not prime, it's 3 times 3. 2 to the 4 plus 1 is 17, that's prime. 2 to the 5 plus 1 is no good, because that's 33. If you think about it a bit, you notice that if we've got a number if we've got a number 2 to the power of ab with a odd, and we add 1 to this, then this is divisible by 2 to the a plus 1. So the exponent can't be divisible by any odd numbers if we want it to be a prime. So we should only take n to be a power of 2. In other words, we should look at numbers of the form 2 to the 2 to the m plus 1. So let's restart. We have 2 to the 2 to the 0 plus 1 is now 3. So 2 to the 2 to the 1 plus 1 is 5. 2 to the 2 to the 2 plus 1 is 17. 2 to the 2 to the 3 plus 1 is 257. 2 to the 2 to the 4 plus 1 is 65537, as you know if you're a computer scientist. And all of these numbers are prime. These are called the Fermat primes. So 2 doesn't really count as a Fermat prime because 0 is kind of a bit of a special case. And Fermat sort of suggested that in fact maybe 2 to the 2 to the n plus 1 was always prime, but in fact this is false because 2 to the 2 to the 5 plus 1 turns out to be divisible by 641. Actually a bit of a historical puzzle about why Fermat didn't notice this, because he was perfectly capable of checking that 2 to the 2 to the 5 was divisible by 641, and the consensus seems to be that he probably did check but just made some sort of numerical error and got it wrong. So Fermat primes turn up in a rather unexpected place. There's a famous problem about which regular polygons can you construct using a ruler and compass. And it's easy to figure out how to construct polygons of side 4 and 8 and 16 and so on because you can bisect angles. And the Greeks figured out how you can construct polygons of sides 3 or 5 or 15. And what Gauss discovered is that if a number is a Fermat prime, then you can construct a polygon with that number of sides using ruler and compass, which is really rather bizarre. And in fact, it turns out the only numbers you can construct with the ruler and compass are ones that are products of distinct Fermat primes times the power of 2. So we have an almost complete list of polygons you can construct by ruler and compass, except that nobody knows whether there are any further Fermat primes. So people have checked the next 30 or so cases and haven't found any further Fermat primes. And it's a completely open question about whether there are an infinite number of these or not. Well, so Fermat suggested this might be an easy way to find primes, but it doesn't quite work. So we can ask, is there any easy way to generate large primes? And this is a sort of open question. I mean, it depends a bit on what we mean by an easy way to generate large primes, since we have some reasonably fast methods that computers can use to generate large primes. But it'd be really nice if we could find, say, a polynomial f of n, such that f of n is always prime. So are there any polynomials f such that f of n is always prime? Well, the answer is yes. It's quite easy to generate these. We can just write f of n equals 3 for all n. It's the constant polynomial. So what we really want is f to be non-constant. Otherwise, we've got a rather trivial answer. So we want to find a non-constant polynomial such that f of n is prime for all positive integers. And you can get pretty close to this. Suppose I take the polynomial n squared plus n plus 41, which was found by Euler. And if you try n equals 0, 1, 2, 3, well, you'll probably find this is always prime for as long as your patience holds up. In fact, it's prime for all numbers n up to 40. However, it's not prime for n equals 41. And it's obviously not prime for n equals 41, because if you put n equals 41 here, this is divisible by 41, of course. So we can get polynomials that try very hard to be prime, but they don't quite make it. So you can ask, is there any polynomial such that f of n is always prime, such that f isn't constant? And the answer is no. And we can see this as follows. Let's look at f of n equals n to the k plus something times n to the k plus something times n plus some constant term. And now suppose this constant term is bigger than 1. Let's call it k. Well, then if we put n equals k, this will be f of n will be divisible by k, because all the terms are divisible by k, so it's not prime. So if the constant term of f is not 1, is bigger than 1, then it can't always be prime. So what happens if the constant term is equal to 1? Well, we can just change f of n to f of n plus k for some number k such that the constant term is not equal to 1, and repeat our arguments. There's no polynomial that always generates primes, apart from the trivial case of a polynomial that's constant. And no one has ever found anything better. I mean, there just doesn't seem to be a really easy, simple way that will always generate primes. Well, we've shown there are an infinite number of primes, but we can ask another question. instead of asking how many primes there are, we can ask how many primes are there less than or equal to x, where x is some number. Now, the number of primes less than or equal to x is often denoted by pi of x, and you've got to be a little bit careful not to muddle this up with the number 3.141 and so on. So pi is the Greek letter for p, which stands for prime. And it's not very easy to find an exact formula for pi of x, and you can see primes are a little bit chaotic, and it would be a bit unreasonable to expect an explicit formula for them, although rather surprisingly, we'll see in a moment there is one. But we can ask, what is pi of x roughly equal to? So we can ask roughly how many primes are there. And Gauss came up with a pretty good answer to this. One version of Gauss's suggestion is that pi of x should be approximately x over log of x. And just warn everybody, since this is a mathematics course, log means log to base e, not to base 10. There's actually no point in taking logs to base 10. So in mathematics, log always means log to base e. And this was finally proved by Hadamard and de la Vallée-Poussin in about 1896, and this is, at the time it was proved, this is probably one of the deepest and most difficult theorems proved in the 19th century. So informally, this means, suppose you take all the numbers up to x, it means about 1 over log x of them are prime. So we can think of this as saying the chance of n being prime is about 1 over log of n. And you've got to be a little bit careful about what you mean by this, because the chance of n being prime isn't 1 over log of n. It's either the chance of n being prime is 1 numbers up to x. It means about, this means, suppose you take all the numbers up to x, it means about 1 over log x of them are prime. So we can think of this as saying the chance of n being prime is about 1 over log of n. And you've got to be a little bit careful about what you mean by this, because the chance of n being prime isn't 1 over log of n. It's either the chance of n being prime is 1 if n is prime, and it's 0 if n is not prime. So it's kind of a little bit meaningless to say what is the chance of n being prime, but whatever. It's sort of reasonably obvious what's meant. So let's have an application of this. Let's ask, is the number of Mersenne primes infinite? So you remember a Mersenne prime is a number of the form 2 to the n minus 1. So what's the chance of 2 to the n minus 1 being prime? Well, it's about 1 over log of 2 to the n minus 1, and this is about some constant involving log of 2 over n. So in order to find out the total number of Mersenne primes, what we could do is we could just take the sum over all n of the chance of 2 to the n minus 1 being prime. So we take the sum over n of k over n, and this will hopefully give us a rough estimate of the number of Mersenne primes. Well, this is just equal to k times 1 plus a half plus a third and so on. And this is the famous harmonic series, which you remember from calculus is infinite. So this sort of suggests the number of Mersenne primes is infinite. Well, fine, but there's a bit of a problem with this argument. First of all, it assumes these numbers are random, and they're obviously not random because they're 2 to the n minus 1. There's another very obvious problem. Suppose we try and ask how many numbers of the form 2 to the n minus 2 are prime. Well, we can apply exactly the same argument, and it suggests there should be an infinite number of primes of the form 2 to the n minus 2. And this is just totally stupid, because 2 to the n minus 2 is obviously divisible by 2, so it's almost never prime unless n is 2 or something. So these probability arguments are a useful guideline to what is true or not, but you should always be really cautious when using them, because they can give horribly misleading answers. A rule of thumb is that in number theory, arguments using these sorts of probabilistic arguments are generally regarded as worth almost nothing, because they're very easy to do, but they're extremely hard to make rigorous. And they sometimes give the wrong answer. And they sometimes give extremely ambiguous answers. Suppose, for example, we try to count how many Fermat primes are there. Well, what we should do is we should take the sum over 1 over log of 2 to the 2 to the n plus 1. Well, the logarithm of this is going to be some constant times 1 over 2 to the n, if we ignore the plus 1. and this is going to be finite, so this suggests there should be a finite number of Fermat primes, and indeed numerical evidence sort of suggests that maybe the ones Fermat knew about are the only ones they have. But there's another argument you could say. You could ask, how many primes are there of the form 2 to the n plus 1? Well, here we would take sum over 1 over log of 2 to the n plus 1, and this is going to be about k times 1 over n, and this is going to be infinite. So this argument suggests there should be an infinite number of primes of the form 2 to the n plus 1, all of which have to be Fermat primes. So we've got two probabilistic arguments, one of which says there should be an infinite number of Fermat primes, and one of which says there should be a finite number, and which is correct. I have no idea, and nobody else really has any idea either. Riemann actually found a rather astonishing explicit formula for the number of primes. What you do is you define the logarithmic integral of x to be the integral from 0 to x of 1 over log of x dx. Well, actually, there's a little bit of a problem with this integral, because if one Riemann actually found a rather astonishing explicit formula for the number of primes. What you do is you define the logarithmic integral of x to be the integral from 0 to x of 1 over log of x dx. Well, actually, there's a little bit of a problem with this integral, because if x is equal to 1, the integral actually becomes infinite and sort of diverges. So when I say it's equal to that, it's not actually equal to that. You need to fiddle around with this a little bit, but I'm not going to worry about this. The logarithmic integral is going to be given by something slightly modified version of this. And Riemann found the following astonishing explicit formula for primes. Well, first of all, he wasn't counting primes, he was counting prime powers. So Riemann discovered that p to the n should count as 1 over n of a prime. So in some sense, 4 is really is sort of 50% of a prime, and 8 is 1/3 of a prime, and is 1 over. So Riemann discovered that p to the n should count as 1 over n of a prime. So in some sense, 4 is really is sort of 50% of a prime, and 8 is 1/3 of a prime, and in some sense. And he found that instead of counting primes, it's easier to count prime powers in this funny sense. So pi prime of x is the number of prime powers less than x, where p to the n counts as 1 over n of a prime power. And he found a completely explicit formula for this number here. So this is just equal to the logarithmic integral of x minus sum over some funny numbers rho of the logarithmic integral of x to the rho. Here the sum is over all these numbers rho, which are some so-called zeros of the zeta function, which I'll explain in a moment. And now this is a really astonishing formula, because these are all nice continuous real valued functions. However, this function here is certainly not continuous, because it sort of jumps by 1 whenever x goes beyond a prime power. So we've got this absolutely astonishing formula of a discontinuous function being given as a natural sum of all these nice continuous functions. Here the logarithmic integral of x turns out to be approximately x over log of x. So this explains why the number of primes less than x is approximately given by this number here. So what are these mysterious numbers rho? The numbers rho, the zeros of the zeta function, which is given by this number here, 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. So for example, zeta of 2 is equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. This is a rather difficult sum to evaluate. Euler became famous by discovering it was actually equal to pi squared over 6. And the numbers rho are the numbers numbers rows such that zeta of a row is equal to 0. Well, there's a bit of a problem here because the known zeros of rho tend to be complex numbers, and they're complex numbers for which this series doesn't actually converge. So we need to do quite a lot of work in order to make sense of the Riemann zeta function of other complex numbers, and then try and work out where the zeros of the Riemann zeta function are. At this point, we come to probably one of the most famous open problems in mathematics, which is the Riemann hypothesis, which just says the real part of any zero row is at most a half. There's $1 million prize for solving this if you ever manage to solve it. In fact, solving this Riemann hypothesis isn't the hard part. The really hard problem is not in solving the Riemann hypothesis, but trying to get someone else to read your solution when you've solved it, because crackpots produce several proofs of the Riemann hypothesis every month. So if you show a proof of the Riemann hypothesis to a mathematician, the mathematician will just throw it in the bin unread, because all mathematicians are sick of getting sent proofs of this. Anyway, Riemann's work gives an astonishingly accurate formula for the number of primes less than a number. For example, the number of primes less than 100 million is exactly equal to 5761455. Riemann's estimate, not counting the zeros over rho, turns out to be 5761522. As you can see, it's sort of already accurate to 4 significant figures. So this is using Li of x as an approximation not to pi of x, but to the number of prime powers. So you have to subtract out the squares and cubes and so on of primes. And if you do that, you get this astonishingly accurate formula for the number of numbers less than number. One of the basic facts about primes we're going to prove is the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says that every integer greater than or equal to 0, so greater than or equal to 1, is a product of primes in a unique way. That means unique up to order. And there's a very nice formula for this involving the Riemann zeta function, which is 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. And Euler discovered that you could write this as follows. It's the product of 1 over 1 minus 2 to the minus s times 1 over 1 minus 3 to the minus s times 1 over 1 minus 5 to the minus s, and so on, where this is a product over all primes. This looks rather astonishing if you see it for the first time, but it's actually quite easy to prove. If you just write each of these factors as a geometric series, we get 1 over 1 plus 1 over 2 to the s plus 1 over 4 to the s plus 1 over 8 to the s, and so on, times 1 plus 1 over 3 to the s plus 1 over 9 to the s, and so on. And now if you multiply out this product of an infinite number of factors, each of the terms you get by taking one term from each of these factors and multiplying them together. So for instance, if we take this term, and this term, and 1's everywhere else, we get 1 over 2 to the s times 1 over 3 to the s squared times 1 over 5 to the s, which is equal to 1 over 2 times 3 squared times 5, which corresponds to 1 over 90. And now here we have a term 1 over 90 to the s. So you see every term in this series here comes from a unique term in this infinite product, because every integer can be written as a product of prime powers in a unique way. So this is Euler's version of the fundamental theorem of arithmetic. It's this amazing factorization for the Riemann zeta function. Euler also used this to give another proof of Euclid's theorem that there are infinitely many primes. What you do is you just take s equals 1, and now you notice this term here is infinite because it's just 1 over 1 plus 1 over half plus a third and so on, which is infinite. So it means this product over primes must be also must be infinite. But this lecture is part of the Berkeley Math 115 course on undergraduate number theory, and is a continuation of the previous lecture, where I'll be giving a survey of some of the things that we might be covering later in the course. So the first thing I'm going to talk about today is congruences. So to motivate this, suppose we have the following question: is 1, 2, 3, 4, 5, 6, 7 a square of an integer? And it wouldn't be too difficult to do this by a bit of calculation, but in fact you can see it's absolutely obvious that it's not a square. The reason it's obvious that it's not a square is the last digit is 7. And if you've got a square number, then the last digit has to be the square of 0 squared, 1 squared, 2 squared, and so on, or up to 9 squared, which is 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. So the last digit has to be one of these numbers here, and since 7 doesn't appear, we can immediately see without any real calculation that this number is not a square. So what this is a special case of looking at things modulo 10, where in general we say A is congruent to B modulo some number n. So this just means A minus B is divisible by m. So this notation was introduced by Gauss and turns out to be very useful. So here we're saying that 1, 2, 3, 4, 5, 6, 7 is obviously congruent to 7 modulo 10, but x squared is not congruent to 7 modulo 10 for any x. So you can look at more complicated versions of this. For example, we can ask, is 1000003 of the form x squared plus y squared for some integers x and y? Again, you could do this just by trial and error, although it'd be a bit more tiresome because there are about 1,000 different numbers x you have to check. However, there's a rather easy way to see this isn't possible, because we notice that x squared is congruent to 0 or 1 modulo 4. So if you've got any square, you can check that its remainder is always 0 or 1. So x squared plus y squared must be congruent to 0 or 1 plus 0 or 1 mod 4, which is congruent to 0, 1 or 2 mod 4. However, 1,000,003 is not congruent to 0, 1 or 2 mod 4, so we can see very easily that you can't solve this equation.